of Edison and Tesla. Tesla, who was the nice guy, he really liked AC, alternating current, which moves backwards and forwards, and Edison, who turned out to not be a very nice person, he really liked DC, direct current, and we're going to look at why Tesla won the battle of the current. It's the 1800s, you've got electricity, you know it's absolutely brilliant. The problem everyone had was, how do you get it into people's houses? How do you transport it from the power station to people's houses? So we've looked at how really long wires cause the electrons to bump into loads and loads of particles on their way and give off a lot of heat. You put a wire in your power station and that wire went all the way to your house. By the time it got to your house, loads of heat had been given off and you're hardly getting any electricity. So Edison's solution to the problem was, well, we'll just have really local power stations, like everyone will have a power station really near them. But in order for his current to work, the power station had to be 1 mile away from the house. Can you imagine, like, every mile there being a power station? I mean, it's just totally ridiculous. Like, some houses in the countryside, they don't even have another house around them for a mile. What are you going to do? Just build a power station next to every house in the country? Like, no, it was a very silly idea. What they needed to do, the only way really to make electricity travelling through a wire more efficient is to make the current lower. So the current is just how much charge travels through the wire every second. If you can make the current really low, then there'll be fewer collisions and you'll give off less heat. But how do you do that? Well, let's go to this model, okay? So yesterday we looked at how batteries give electrons energy, electrons carry that energy through the wire, give it to the bulb, bulb lights up. It's quite similar to a pizza shop, and pizza delivery people, and a house. So the pizza delivery people are the electrons, and they pick up the energy, pizzas, from the pizza shop, and they carry it to the house. So the current would be, the current is the amount of charge per second, yeah? So the current would be how much charge is like passing this point each second. Voltage is how much energy each electron is carrying. So in this model, voltage is how much pizza each delivery person is carrying. Power is the amount of energy per second, and that's what you want. You want to get lots of power into the houses. So you want the power travelling through the cable to be the same, but you want the current to be nice and low. So how do you do that? In order to keep the amount of the energy the same, but have less current, what you could do is just put more pizzas on each pizza delivery person, right? So the pizzas are the energy. If each pizza delivery person is carrying more pizzas, if each electron is carrying more energy, you need less electrons. So 2 electrons carrying 2 pizzas is the same as 1 electron carrying 4 pizzas. I am really getting my metaphors mixed up. Izzy wants to know why the pizza delivery guy leaving the house still has pizza. Good point, Izzy, thanks. No, that's not right. The power is how much energy passes this point per second. So you could have 2 bikes carrying 2 pizzas going past this point every second, and that would get 4 pizzas past the line. Or you could just have 1 bike carrying 4 pizzas, and that would get 4 pizzas past the line as well. And how many pizzas each bike is carrying is this model's voltage. So if you make the voltage higher, put more pizzas on the bike, then the current, the amount of bikes, can be lower. Power equals current times voltage. If you want power to stay the same and you want to make current lower, you have to make voltage higher. Now, you can't do that with direct current, or you certainly couldn't when Tesla and Edison were going. But it turns out that Tesla's kind of current, AC, you can step it up and step it down with something called a transformer. So what happens nowadays is that electricity comes out of the power station and it's produced, and it's about 25,000 volts, which still sounds like a lot, but it gets to the transformer and the transformer steps up the voltage to 40,000 volts. But that means that the current is really low. So each electron is carrying loads of energy, so there's not many collisions in the wire, and those electrons carry loads of that energy all the way to your house. But obviously you don't want 40,000 volts in your house. That would be horrific. So another transformer steps the voltage down to about 230 volts, and that means that you've got plenty of current but a much safer voltage coming into your home. And that is why Nikola Tesla won the battle of the currents. Although still had a very sad life, as you will see if you watch my story time we did yesterday. So how fast do you think the electrons are travelling through this wire? Okay, think about like when you press a switch on a torch, how long it takes to come on. What would you say how long it takes the electrons to carry the energy through the wire? I imagine that you'd think it would be very, very fast. But it's actually surprisingly slow. Electrons actually only travel about 4 centimetres per hour through a wire. So it's not like they shoot out the battery and carry their energy to the light bulb and give it off. It's the battery actually sort of sets up an electric field, and the electric field is kind of what sort of carries the energy really, so the energy like travels at the speed of light. Oscar age 8 having a sleepover at your grand's house. Nice, your grand watching this as well. How the battery sends out electrons, good question reading the sound. So the electrons are already in the wire. So metal is that's why we use metal for wires, because it's got loads of free electrons in it that aren't attached to their atoms, they're just sitting around. So as soon as you attach the battery, then the electrons in the wire start moving. But thank you for saying that, because a lot of people think that the electrons are stored in the battery and they like fly out, but that's not what happens. Amelia and Sam would like to know if you can see electrons. No, they are so small, they're absolutely teeny tiny. They've hardly got any mass at all. Because they're fundamental particles. They're not made of particles, they just are particles. Why does it take a double wire? Why does it take a double wire to get electricity in the light bulb? So the reason there has to be a wire on this side and a wire on this side is because electrons need a reason to move. So it's another word for voltage is potential difference. It's sort of analogous to dropping something. So to make something move, you've got to lift it up. It's got to have a sort of reason to move, if you see what I mean. Like, that's not going to move. You've got to give it the potential to move by lifting it up. So we'd say that there's a sort of difference there, isn't there? There's a difference in height and therefore it moves. It's kind of the same with an electron. You need to have something different on this side and different on this. You need to have something different on either side of the electron to make the electron move. And the difference is the sort of electrical potential difference that this battery creates. Eileen, if it only moves 4 centimetres per hour, how does a torch come on so quickly? Timothy, I know, right? If you're thinking about that, you should probably do physics at degree level. It's kind of like, you know, when you turn on a tap at home, you don't have to wait for the water to like travel along the tap. There's already loads of water in the pipes. It's kind of the same as this. There's electrons in the wire, so the energy can get there straight away. Or if you imagine a massive traffic jam, as soon as the lights turn green, a car does pass this point. It's kind of like that. It's not like this electron here has to get here. If you imagine there's a traffic jam piled up here, then as soon as the battery's connected, this car kind of crosses the line. Bye, Isaac. Joe, I can't believe you're thinking about pizza. What is wrong with you? Oh. Amelia, what a brilliant question. Are there electrons in everything? Yeah. So atoms make up everything in the whole world, and atoms are protons, positive particles, with electrons, negative particles, whizzing around them. So yeah, they are in everything. Well, except protons. Electrons are what we call fundamental particles. That means there's nothing inside them. Protons actually have other very awesome particles inside them, which you might learn if you do physics at A level. Bye, have a nice week.